basically where Emmanuel left off. So he was telling you about the big open questions in the field of MBL, and you know, if you talk about the 2D Fermi-Hubbard model, you don't get around talking about big problems in some sense, right? Because so you know, okay, so the model we're going to discuss today is this 2D Fermi-Hubbard model. It looks exactly the same as this 1D one, except that these guys are vectors, and we look at the 2D square lattice. And you know, most of the things we know about, or we think we know about the Fermi-Hubbard model in 2D, is really from the studies of high TC cuprates. So there is, okay, of course, some limiting cases are pretty well known, but you know, many of the interesting features are widely believed to be true because these models are believed to describe these high TC superconductors. And so I want to start by basically walking you through the phase diagram of this 2D Fermi-Hubbard model in these cuprate materials. So the idea is not to, you know, go into all the details. So I guess you've heard of this story. There's the super complex phase diagram which shows, you know, rich phases. And I just want to give you a basic idea of the key phenomenology that people find in the different regimes. And of course, you know, I won't be able to give you an exact understanding of all these things. And there is no real complete understanding of all these things, right? But just to give you an idea what types of physics you see. So first of all, keep in mind the axes are like this. This is the doping, this is the number of holes, and we start from 0 doping, and this is the half-filled case. And we work in this regime when the Hubbard U is large compared to the tunneling, which means that the system prefers to form a Mott insulator, right? So this is a Mott insulator with 1 Fermi per side, and then you increase the number of holes, and you get these interesting phases here. In particular, the high TC superconductors here, and this is temperature, okay? And so now we're going to walk through this and discuss the key phenomenology of these phases. At half filling, we know there will be spin exchange interactions. They are antiferromagnetic, so you actually expect an antiferromagnetic phase as long as you don't have, let's say, don't have any or very few holes, okay? And in the sketch, this pattern looks roughly like this, okay? And I think Immanuel Bloch yesterday showed you that in Harvard they have realized long-range antiferromagnets even in cold atoms, so that's basically been said. There are still some open questions. I don't want to go into details here. One thing I want to do though is talk a little bit about how classical this 2D antiferromagnet is, because I feel like there's some, you know, confusion as to how quantum this ground state is, right? So the idea is, of course, if instead of these Heisenberg interactions you had just Ising interactions, then the ground state you can actually write down as the classical Néel state, which is this perfect up-down, up-down, up-down state. And okay, so this is a sketch here in one direction, but of, you know, the same holds true in 2D, right? So think of this as a 2D perfect checkerboard. And now, of course, we know that the spin exchange interactions, so what they do is, in fact, if you have S1 dot S2, and you apply this onto a state up, down, let's say on two sides, you get a superposition of up, down, and down, up, right? So that means these interactions tend to exchange neighboring spins, and that means if you start from a classical Néel state, these spin exchange interactions will mess it up, right? Because if they start to exchange these two guys, things will go wrong and deviate from this classical pattern. Okay, now what's a good way of telling how quantum this ground state is? Well, one thing you can do is you can look at the full counting statistics of the staggered magnetization. Okay, so what I mean by this, first of all, staggered magnetization is you take your spin operators as JZ and you sum them up, but you basically introduce minus signs on every other lattice side, right? And this basically reflects this classical checkerboard pattern. Now, of course, if you take a classical checkerboard pattern, this classical Néel state pointing in some direction, Z, let's say, and you look at how many counts you get for which staggered magnetization, if you take many snapshots, well, you know, all the time you get the maximum allowed staggered magnetization, right? Because it's perfectly matched. Okay, so the histogram you would get looks like this. And now, of course, the interesting question is what happens if I take the same plot and I look at the ground state of this 2D Heisenberg model. And here's the result. Okay, so this is a calculation based on some variation wave function. But what you basically get is this is again the staggered magnetization. This is the probability to get a certain value out. And one thing I should say is in this variation wave function, we break by hand the symmetry. So and that's established. It turns out the ground state of this antiferromagnetic so it spontaneously breaks this SU2 symmetry. So it does favor one particular direction. And what I did now is I took this direction to be the z-axis, okay? And then you can see that indeed still, as before, most of the counts are actually at some positive staggered magnetization here. And then there's a certain width, right? So sometimes you also see other values of the staggered magnetization. Now, this is a 10 by 10 system. Turns out the width of this peak here is actually related to the finite size, or the size of the system. If you go to a larger system, you expect that the width here should scale down. The other thing then you can ask is, well, so how can we tell? So how quantum is it? And the point is, the average value here, that basically tells you how quantum the model is. Because it tells you how often these spin exchange terms are able to destroy the perfect checkerboard pattern. And if you look at the mean value here, it's something like maybe 7.5. But I don't, at this point we don't care about the exact number, but clearly this is a number which is fairly large and somewhat close to 1, okay? And in this sense, I would argue that this ground state of the 2D Heisenberg antiferromagnet is actually a fairly classical state, okay? Quantum fluctuations do play a role, but it's not completely bad to think of it as a nil state with some noise on it. Okay, so let's move on in this phase diagram. If you go to higher dopings and at some high temperatures also, you get into the pseudo-gap phase. Now, the key, I don't have time to go into the details, but maybe one takeaway message is the interesting features of this phase you get if you look at ARPIS spectra. So you basically ask for the low energy states of the electrons, or the holes in the system. And the key message is they basically find an interesting arc here. And so one thing to keep in mind is if you had a Fermi surface, so if these holes doped into the system would form a normal Fermi surface, you should see some closed structure here. But these ARPIS spectra only show half of it. They show this arc, okay? So this is puzzling. We don't really know why the backside is missing. And what's even more puzzling is that if you look at the, if you say, okay, maybe for some reason we just don't see the backside of this surface, but let's assume there is a surface and just the signal is too weak here to see it. Then the volume of the surface should be like this. And if you turns out if you plug in numbers and look at this volume, the volume of this putative Fermi surface here is way too small. And so this is actually telling us something about fractionization. I don't have time to go into this, but so these are the puzzles that people are asking in this pseudo-gap phase. Okay, moving on, we find a crossover to a strange metal phase. A strange metal is characterized by some non-Fermi liquid transport properties. Basically, the resistance scales with temperature. I don't want to, again, go into details, just mention that in Princeton, Wasim Bakr has recently measured this. So that's also something that articulate atoms can already access. And I'm sure we will see a lot more progress in cold atom experiments in unraveling what the physics of these phases is, and it's really not completely understood. Okay, at lower temperatures here, some of these cuprates, not all of them, show density waves or stripe phases. And a naive way of thinking of them is as follows. So you can think of some antiferromagnetic pattern on this side, and then there's a region of high hole density. So that's indicated by this gray envelope here. And if you go across this line of high hole density, the sign of this AFM pattern actually flips. This is exactly what Emmanuel has shown you in 1D, where you basically once you cross a single hole, the antiferromagnetism includes the domain wall. So in some sense, these stripe phases here are 2D versions of this 1D phenomenology. And there's lots of discussion as to how important these stripe phases are for the high temperature superconductor and these interesting normal phases of the cuprates up here that don't have order parameters. And it's really not known. Some people say they're very important, other people say they're not at all important. So, that's an open question. Next, from the strange metal, we can continue on to the Fermi liquid. This is again a crossover. This is not such a strange phase, you could say, right? Because if you imagine you go to very high doping, you have many, many holes, then it's probably not so clever anymore to think about holes, right? Because what you have is just once in a while you have a fermion, right? And then you could say, well, these fermions simply form a Fermi sea or Fermi liquid, and this is basically what happens at high doping values. So here you should really think about the actual fermions again. So this side of the phase diagram is believed to be much better understood. but still there are some interesting questions what exactly the effect of the interactions is and how we can understand that. And finally, of course, there's the high-TC superconductors. Again, if you approach this dome from the high doping side, it's fairly not as unconventional as one might think, and the BCS description is not so bad. So you can basically, this side of the superconductivity is not so surprising. What's really surprising is basically, or really poorly understood, is how you should understand the formation of superconductor coming from this side. And also, if you look at the basically properties of these BCS superconductors, on this side they're much less described by a BCS theory. Okay. So this is the overview of the phase diagram. I think the key open questions in the field right now is how can we understand the destruction of antiferromagnetism at low doping? This is really poorly understood. There's no well understood field theory, and it's also really basically unknown how long it is really important to have antiferromagnetism. So it's clear that there are some decent antiferromagnetic correlations surviving as you go here, but it's really not clear how long the system is sort of close to this antiferromagnet at low doping. And related to this is also the question: what are actually the carriers of charge in this regime? And of course, that's a question we now start to address by looking at single holes and the antiferromagnet and so on. Okay. So let's pause with the slides here and try to understand in more detail, how we should think about these holes. And first of all, I want to simplify life a little bit and go through details through a simpler model. And the idea is really to understand the properties of these holes moving through these 2D antiferromagnets. And to do this, we will look at this so-called TJZ model. So do you prefer the blue or the brown pen? Brown? Okay, brown. Cool. Okay, so the TJZ model, the idea is simply, we've seen yesterday that if you take the TJ model and you have this large U, you basically get these Heisenberg exchange interactions, right? And we also discussed before that those are a little bit complicated because they introduce these quantum fluctuations. So the idea in the TJZ model is to keep them simpler and work with Ising interactions. So we're going to write the TJZ Hamiltonian as sum over nearest neighbor lattice. I won't write these vectors, right? But think of these guys always as vectors. And we'll have some JZ term. And I only keep the Z part of these interactions. And so this term alone will simply give us a classical Neil state. Okay. And then, of course, we still have the tunneling of the holes, and we have the story from yesterday. So we have the projector on to the singly occupied or zero or not zero. So this means max singly occupancy. And then we have the hopping terms, as usual. Okay. So let's look at this model. Okay, and so the question I want to ask you now to think about, and I don't expect you to just see the answer, is if I take a single hole inside this antiferromagnet, right? So let's say we start with this state here. It extends all the way. First of all, can this hole move or to any point where it wants? That's the first question. And the second question, if it can, what's the dispersion relation? Okay, so what do you think? Can it move? So one argument, of course, you can give is this sketch that Thierry gave yesterday, and where the idea is you introduce a hole and you move it around, and of course once you move around the hole, you mess up these spins, right? And then you basically introduce a string of spins that are on the wrong sublattice, okay? And that will cost energy, right? And okay, so let's write this down, right? So let's look at this in some detail, right? So let's introduce some little formalism, right? So I will always write the undoped state as psi naught, okay? So this is the antiferromagnet without a hole. And now we're going to look at the first state. I call this CJ So this is the state with a single hole. That's our starting point. And now we can construct one first set of states, and I will label them with this string here. Okay, sigma. And let's consider straight strings for now. Okay, we just assume the whole hops in a straight way until here, right? So we started here. Right. So here we had the hold on. Mess this up. So we had the downspins starting around where the hole started, right? And so now we have these downspins left over, and then of course here we have these up downs. But we also have up downs here. So it looks like this, right? And this state I will just label this by this string trajectory that we had. So I'll say, okay, I call it this, well, you'll see why, but I call this JS, this initial state, just the index. So this new state I will label by the initial state JS, where we create the hole, and the string. Okay. And again, let's say the string at this point is just linear, and then it has a certain length, right? Okay. So now, of course, we can look at this and basically figure out what the energy of this state is. And of course, the energy you get by basically summing up the spins that are happy. That's easy enough. That's those. Okay. So obviously, the energy you get will be proportional to the length of the string and the JC, right? So we'll get E of L something like proportional to L times J squared. Okay? And you can work out the prefactors and so on. So for straight strings, this is actually true. Okay? And so now, at this point, let's ask again, does the hole move? Now we would say, well, of course, if we have a potential, which looks like this, right? This is the length of our string, and the potential keeps growing. And I start from 0, probably the hole is not going to move far, right? Because it basically hits this wall, and then it will just return. So then one would argue it cannot move. Okay, what do you think? Will it move in the end or no? I mean, clearly it moves in this TJ model, right? But this is like a more tricky model, TJZ. So it could be that since these spins are so classical, maybe it just doesn't move. Well, it does move, right? So what do you think? Well, how could it move? So one thing, of course, we did so far is we only looked at these straight strings, okay? Now, it's fairly easy to look at other strings as well. And of course, some of them are fine, right? If you look at, say, you start at this side and you make the string go like this, right? The energy will still increase. Maybe when you do these turns here, the energy will not, depend exactly linearly anymore on the length. It could also be, if you look at strings like these, that, now these guys are neighboring, so the energy could actually be a bit lower, right? And okay, so it turns out if you play with some of these states and you look at the energy of these string states, you find, yeah, indeed, some of the strings give us energies which are here, right? Somewhat below this linear line. But this, of course, is not enough yet to move, right? Because it's still, the average here keeps increasing, right? But then, of course, there are some very special strings, and those are loops, right? So you can already imagine that loops are special, right? And so it turns out there's one particular kind of loop called the Truckman loop. And so that's because Truckman basically introduced it. And the idea is to do the following. Imagine I want to make sure everyone can see it, so maybe we'll erase this and put it there. So the Truckman loop goes like this. You basically start at this side, and you make the whole go like this. Okay. Now, of course, you guys can all draw some checkerboards and do the game, but what you'll find is actually that this state is equal to the state where we just basically started the whole on this side. Okay. So it basically, you can draw it down, it's easy, but it turns out if the hole does 1.5 loops, it can basically move from here diagonally to here without destroying the antiferromagnetic spin background. So the antiferromagnet in the background is exactly, stays the same. So in fact it looks as if the hole would just freely hop on the diagonals, right? Do you believe me, or shall we go through this? Yes or no? Okay, I guess you believe me, right? If you just draw the spins, you move this path, you'll find that this spin effectively just moves diagonally here, the hole moves up here. Okay, good. Now, this of course means that the hole can actually move, right? Because it turns out that this loop, we found one particular loop that again goes back to zero energy, right? So one particular string state, has zero energy here, but also, and the length of the string is 6, right? Because we did 6 hops. And of course, if we have one of these loops, we can have infinitely many, right? So that of course means that the hole can in principle move to any point in the lattice, right? Because we can just repeat these loops once, over and over. Okay. So now the question is, we basically answered the first question: can it move? Yes, it can. So the next question would be, what's the dispersion relation of this hole? Yes.
Sorry, for the Trugman loops, do they have to be around the boundary? They don't have to be around the boundary?
Oh, sorry. I'm always thinking of this as being embedded in an infinite system, right? There's no boundary.
So then I don't think I understand. So like the top, for example, the top line, don't you flip like? I think it might actually be.
Okay, we will
draw.
Yeah, we'll draw it. Okay, so the idea is to start with the hole here, let's say, and up and down, up. So this is, and we call this state string length 0, right? And then the next, let's say we do this loop, right? We start here and go this way. So the next state looks like this, right? And of course, there's a bunch of spins around, but I won't affect them, so I don't need to really draw it. Okay. Now the hole moves here, so this upspin goes here, right? Up, down, okay. And then the hole moves there, and then there. Okay, let's skip one step. So then it ends up being here, up, down, up, right? So here this is the first, and this is already this one, right? And now we continue. Let's do 2 steps again, because we're fast enough, right? So now this upspin goes up here, this downspin goes over here, hole is here, right? This one stays where it was, so now this is actually this state already. And now I think we just have, one more, so the hole goes up here, right? And you can see it's up, down, up, and the hole is here. That's the full thing. And now if you look at it, right, there are upspins here, and there are upspins again, right? Okay. Cool. More questions? Okay, now the question, what's the dispersion relation of the hole? Well, of course we would say that the hole can hop diagonally, right? So the center of mass of this hole should basically be able to hop diagonally, which means that if I write down a tight binding dispersion for this guy, one of the hops is in positive k direction plus positive y direction, and the same, of course, in negative direction. So this term is the diagonal hopping here and here. And then, of course, we have another term, which is the diagonal hopping here and here, which is cosine kx minus ky, right? And there will be some prefactor, and I call it T Truckman, okay, TT. Okay? And it's called Truckman because these hopping processes happen through these Truckman loop processes, okay? Okay, so now the next question is, does it make sense for you? Just a basic type binding. Okay, so now, what do you think, how large is the T Truckman? So there are two energy scales in our problem, right? One is Jz, and the other one is T. So will it be proportional to one of those? Okay, so it turns out this is actually tricky. So the result will be that this T Truckman is much less than the tunneling T, and the idea is the following. So now we should, really take care about of the entire Hilbert space and ask how often does this actually happen, right? And so the string Hilbert space we just constructed looks as follows, right? So I want to now define the basis for you, right? Now the basis states, I have to label them somehow, and I already told you before we're going to call them JS, that's where we started. And then we have the string, okay? Now, let's fill this whole thing with some life, or some physics. Why do I call it JS? Well, the idea is to draw some analogies with 1D, right? In 1D, we knew what happened was we had a spin chain, we put the hole there, we create the hole, and then the hole, let's say, moves away, but what it leaves behind is a spinon, right? And so here it's actually a very good way of thinking about this is to say that, actually this sort of defect that the hole leaves behind when it draws the string, this configuration basically in the TJZ model, this is what we think of as a spinon. Okay. At this point it's really just a name, right? So, but what is true is actually that it sort of corresponds to a fractional spin excitation, right? Because what we did is we took a 1D line, and along this line we moved all the spins by one side. So we can actually think of this defect at the end of the string as a spinon, and then there will be the string sigma. And of course, this was the initial point where I created the hole, right? So this is actually the position of the spinon. Okay, so that's why I call this J spinon. Okay, and then we have a bunch of strings sigma, and of course there are many. So the strings are of course a bit, there are many of them, right? And in fact, the space of all the strings you can actually think of as a beta lattice, right? So the beta lattice is defined as follows. So this is, let's say, the trivial string of length 0. And then at the first hop, the hole has 4 options, right, where it can go. So we have 4 new states here, 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 and here. And let's say it hops to the right, as it did here, right? So now we will be at this one particular string state here. And from here, it has 3 more options, right? It can go up, further here, or down. If it goes back, of course, it goes back to this original state, right? And so that means we have 3 more states here, right? And then, of course, the story continues, right? And you get this whole fractal lattice of different string configurations, right? So what we can say is that the string configurations live on this beta lattice. Okay. In fact, if we think about our TJ Hamiltonian or the TJZ Hamiltonian, we know that there will be hopping terms of the hole, right? And of course, this means that if we think of this as a single particle problem here, what's going to happen is that the hole will always tunnel between these different string states, right? The string will be strongly fluctuating. Okay? And our basis states will be exactly these guys, where these sigmas are chosen from this beta lattice. Okay? Cool. So now, we have the spaces, and we also have an effective Hamiltonian in the spaces, right, which is this hopping on this beta lattice. But now, of course, we have to be a little bit more careful. Question is, how good is this basis, right? And, well, what do we have to ask or to do to judge if this is a good basis? Well, first of all, we have to ask, are these states orthonormal, and do we have exactly the right number, or do we have too many or too few, right? Now, of course, these states will be, most of them will be orthonormal, right? Because many of them have different hole positions, and if the hole position is different, they will be orthogonal, right? If they have the same hole position, but they had different strings, connecting them, they will also be orthogonal, right? Because I can tell that one state has a different spin configuration than the other. So in fact, now we get to these Strugman loops again, that the basis is over complete. And the idea, of course, is again to draw loops, right? In fact, so if we draw some pictures again, right? So this state here, we call it the state with the spinon at this side, right? And there will always be 4 sides, right? And we saw that this state here, and okay, let's add the string like this, okay? So this is the state we get if we start with the spinon here and move the whole to here. And then, but then we actually said that this is exactly the same state we would get if the spinon was here and there was no string, right? So the way I wrote these down here with the beta lattice, I sort of pretended that these 2 states are actually different states, right? But we also see that in fact they're not, right? They're the same states. And of course in the same way, you know, there will be quite a number of loops that I can construct, which are basically overcomplete in my basis. Okay. So what do you think, how bad is it if we basically assume that these states, we basically just assume that this state is orthogonal to this state? Well, so now you would say, well, you know, we have exponentially many states in our Hilbert space, right? And in fact, the number of these string configurations grows like 3 to the L, right? Roughly, because every new L I have 3 more options. And the number of loops is much smaller, right? Because in fact, even to get the first Druckmann loop, I have to do 6 hops, right? And that means I have of the order of 3 to the 6 states already, and only 6 out of these 3 to the 6 states are these loops, okay? So in fact, these loops are a very small fraction of all the states, okay? And now, okay, now maybe let's do a little jump, okay? And so I want you to basically think about another model where you do tricks, where you play tricks with orthogonality, okay? And these systems are type binding models. So imagine you have an I here and an I here, and you want to calculate the effective hopping element of the electron from one to the other, right? Actually, what we do is, what we like to do is actually draw one of the atomic potentials, goes like this, right? Solve the wave function, which goes like this. And then we have another atomic potential, which goes like this. And this potential, right, which goes like this and has a second wave function. And of course, we know the tunneling matrix element in the end has to do with this overlap of one of the function with the other one, right? But the way we treat this problem is exactly, it's kind of similar, right? Because what we would do is we first solve the problem of this wave packet in the presence of just this one potential, and then we treat this as a completely different state, orthogonal, solve this wave packet, and then we sort of glue them back together, right? And calculate the overlap. And it turns out that the exact same thing you can do with these loop configurations. And this is actually a constructive way of basically getting a type binding expression for this Druckmann loop thing. And of course, if you look at this type binding thing, right, the reason this works is because this number here, the probability to go this far is very small, right? So we treat that's why this basically works as a perturbative approach, because the probability that this electron even comes here is very small. In fact, the energy difference, right, when, let's say, if it is here, the energy difference, so how much this potential, the actual potential deviates from the assumed potential, the energy difference is large. But the probability to get there in the first place is small. And the exact same thing happens in these Druckmann loops, right? Because we have exponentially many strings, and just because the tunneling is fast, right, our chargon, or this holon, will delocalize over all these strings, so they are basically fluctuating around. They're exponentially many, and it's only these few loop configurations that allow the state to hop from this state to this state, right? And that's why this type binding description is actually very accurate, it turns out. Okay, does this make sense to you? So I want to now basically put forward a little bit different interpretation, right? So far we basically discussed the hole, right? And we said the hole is moving around, and the hole can hop diagonally. But we also actually saw that mostly what the hole does is it is fluctuating on all these different string states, right? Because remember, the tunneling T is much bigger than Jz, right? And that means in order to have a low energy state, the hole has to delocalize over all these states, right? if we just forget about the loops for now, then you would say, actually what happens is we have the spinon at this initial site, and then we have this strings, and we would say, actually what happens is exactly what Thierry said the other day, right? That the chargon is actually bound to this spinon by the string, and it's much like a molecule, right? Where or like partons, right? So you have one parton here, and this parton is simply bound to this other parton by the string, right? So this is a very nice language. And now, of course, if you come back to this case here, to these loops, what you realize is actually, if you ask what is actually hopping, what's hopping is not the whole, right? I mean, the whole is hopping all the time. It's delocalized over all these string states all the time. But what's tunneling diagonally is actually the spinon, right? Because effectively what happens is that the spinon goes from here to here. And this turns out is a much nicer interpretation. So just to maybe wrap this up here. What we see then is that if we have a single hole inside this TJZ model, we should think of it as a bound state of the spinon. And hold on. Okay, now think of it, phenomenologically. And of course, first thing we would ask, what's the mass of this of the spinon, right? The mass of this spinon should be given by 1 over the T Truckman, right? That's always the relation between tunnelings and masses. Now we know that the T Truckman, because it's only this exponential, these few loops out of exponentially many states, T Truckman is much smaller than T, right? So this is much larger than 1 over T. But of course, T, that's how fast this charger moves around on the string lattice, right? So this is basically going to be, scaling the mass of the charger. Okay, and if you think about it phenomenologically, you have a heavy spinon and you have a light chargon that's flying around. This looks a little bit like, atoms, right? Where you have a heavy nucleus, and then you have the light electrons flying around. And, they form a bound state. The binding mechanism is this string. But you also know in a nucleus, right, the center of mass motion of an atom is actually determined by the center of mass motion of the heavy nucleus, right? And the same thing happens here, that the Truckman loops will basically move the spinon. And then this entire bound state can move around. Okay, and so the reason I like this picture is because, of course, it can also be applied in 2D, and so that's what we're going to discuss next. Maybe one last thing we can derive here is the following. Now, what we can ask now is what are the properties of these bound states, right? So that's a little bit like doing spectroscopy, right? You basically have your atom and you want to understand precisely how is the electron bound to the nucleus. And there too, usually what you do is you do Born-Oppenheimer, right? So you basically pin your nucleus and then you solve the problem. You say it's so heavy that it's basically stationary, and then you just solve the problem of your electron going around. And in much the same way, what we can do on this beta lattice, we can say, let's pin the spinon. It's so heavy that it doesn't do much. And then we just solve the problem of our string fluctuating around. And it turns out here we actually allowed to solve this problem, assuming this perfectly linear potential, right? So this is our potential, and this will be the string length. And right, and so of course now, what happens is that our bound state will look somewhat like this, right? And so it turns out, and that's what the expression that Emmanuel alluded to, if you now ask for the average length here of the string, there's an interesting interplay between this potential, which is like L times Jz, and the tunneling T. And that actually, if you just look at the, for instance, you write down the effective Schrödinger equation here, you will find that the typical length here scales as T over J to the 1/3. Okay, and that's the one thing that Emmanuel mentioned. It's a simple consequence of the linear scaling of the potential. Whenever you have a linear potential, you get this 1/3 power law for the average length. Okay. Good. Okay, so now we'll take some time and move on to 2D. Any more questions until here? so then I'll switch back to the slides. Okay. Now in 2D, you know, much of the things we did you can do in a similar way, right? So the basic picture we expect is that there should be a spinner, and it should be still bound to the charger, probably by some string, okay? And the first thing we want to discuss now is the properties of these strings, and even how we want to define them, right? And there's an idea here that's related to what we did yesterday. So remember in yesterday's lecture we looked at 1D systems, and we said, oh, actually we can simplify a lot this complicated Hamiltonian by relabeling our spins. So, and of course what we said is we basically first labeled the spins basically in the absence of the hole, and when the hole was moving, we said, oh, now the spins change their position, but we keep the old labels of the spins, right? That's the essence of the squeeze space. And now we want to do exactly the same in 2D, right? And so the idea is shown here, right? So imagine these are the positions of your spinons, the green guys. That's where we basically create these holes. And the red guys here, those are the labels of our spins. And we're going to keep those labels, right? So for instance, if you look at this spin here, right? It was, before this hole has moved along the string, it was actually sitting on side 2, 4, right? That's here, 2, 4. But now that the hole has moved across along the string, it's actually sitting on this side, right? But what we're going to do is we're going to keep the label. And the idea is, this is nice, right? Because imagine you have an entangled state, which is so of these spins, right? Let's say they don't form this perfectly nice product state anymore. Then, if I take the holes and move around these spins, I basically keep this entanglement, but I only take into account that the positions of these spins actually change while I move them around. Okay, so what this leads to is basically a description where the wave function of this bound state of these spinons here and the chargons here will be a product state, assuming that we can do a Born-Oppenheimer ansatz again. And that means that the tunneling, the T is much bigger than the J, right? So there's a separation of time scales. The spinon is heavy, the chargon is very light. And then we can basically write a product wave function where this is the string wave function, and again we're going to assume that it lives on this Bethe lattice that I was drawing before. So we label the states in exactly the same way. And then we can write it as a product wave function with the spinon part and with some background part. And for the background we will usually just assume that that's the undoped Heisenberg antiferromagnet. Okay? And so it turns out if you do this ansatz you can learn a lot of properties about this bound state. So you can for instance ask how do the properties of the bound state change as you increase the temperature. So what this actually does is, if you increase the temperature, the spin correlations in the background will be reduced, right? But that means, if the hole moves around, it's actually much easier to move, right? Because there are less correlations in the background. And that means at higher temperature, the potential will actually be lower, right? And it turns out, in this simple model, that only what you get is a string tension, basically. So the energy is L times 2J times C2 minus C1, okay? Where C1 are nearest neighbor correlations and C2 are diagonal correlations. Okay, yeah. But what this means is once you know the properties of your background spin system, you can learn all the properties of this bound state. Okay, maybe one thing you might find cute or not is this is in some sense related to quantum gravity, right? And in the following way. If you think about it, right, what we're doing is the string wave function. Here, it really describes the coherent superposition of different geometric orientations of these lattice sides, right? And if you think about gravity, right? Gravity is about curvature of space, and that means a reconfiguration of space. And that's exactly what we do, right? We have a coherent quantum mechanical superposition of different relative orientations of these spins that we always label by the old coordinates, right? So that's something we're actually trying to pursue right now to make this more formal, but you know, it's some interesting connection. Okay. So now, again, the key pictures, we have the spinon and these chargons are quickly moving around. And I told you we can learn something about these bound states. And the first thing we can learn in the sketch is why these diagonal correlations that Immanuel showed us today, that they measured, why they go negative. And so here's the idea. Imagine we start from this state where the spinon and the chargon are basically on the same side. And then we have correlations in the background, and these correlations we call the correlations in squeeze space, right? So these are the correlations between the spins before any holes have moved. And let's look at these two spins, right? They are strongly anti-correlated because they're nearest neighbors. So there will be a nearest neighbor squeeze space correlator. And now, when the hole is moving around, it actually shifts this spin over here, right? But that means these two spins, which used to be strongly correlated on nearest neighbors, now are strongly anti-correlated on the diagonal, right? And that means what used to be a nearest neighbor C1 squeeze space correlator now becomes a diagonal correlator in the lab frame if we take an image like this, right, in this configuration. And of course it also goes the other way around. The C2, the diagonal ones in squeeze space become nearest neighbors, okay? But what this means is if you now look at this hole here, and you look at the diagonal correlations around the hole, those are the correlations that used to be nearest neighbor and therefore negative, right? Because it's you know, red and blue, they used to be diagonal before the hole has moved. Let's go back. And they used to be next to each other, now they become diagonals. And that's exactly of course what they observed in the experiment, right? That these diagonal correlators here around these doublons go negative if these guys are mobile. And you saw these slides before, right? If this doublon is pinned, this doesn't happen. Okay. So those are these guys. Good. So now, let's see how much time we have. Good. Okay. So now you can say, you know, I talk much about these strings and these string patterns. And so now, of course, an obvious question is, can we detect these string patterns directly? And in principle, these quantum glass microscopes are like super well suited to do that, right? Because they can basically take snapshots, and the idea is to look in every single snapshot. And if this picture is true that I'm drawing with the strings, in every single snapshot we should see a bunch of these string patterns, right? And you can also see that it's important to look at individual snapshots, because if you average over all different snapshots, you would always average over all these different string configurations, right? And even if every single snapshot has one particular string configuration, you know, one's like this and the other one like this and like this, if I average over those, it just looks like a liquid, right? It's completely blurred out. So then we would basically lose the information about the structure. Okay, so now I want to show you some results, how you can actually detect these string patterns. And the way we do this is pretty easy. So we look at a snapshot like this. Okay, so we basically see up and down spins, and sometimes there's a hole, and there's some noise, right? If you look at this, this is not a perfect checkerboard pattern. But to find out how different it is from the perfect checkerboard, what we do is we take this snapshot, we subtract the perfect checkerboard, and what we get is this thing on the right, where all these green, these red plaquettes are sides where the spin is not oriented as it should be in the perfect checkerboard, and the white ones are happy, right? They are exactly the right way. Okay. And of course, what you can see is that now, next to the hole in the middle here, sometimes, and in fact quite often, you find that there are some deviations, and those we call the string. Okay. Now, of course, you have to be a little bit careful, and you can see it here already. There's noise in the background, right? So we will, even if the holes do not move, we will always find some noise and some strings, right? So if I draw these strings, that's the sort of the strings I analyze. Those are not necessarily exactly the same strings that we label in our basis, right? But the idea is that they should be related, right? And now we're going to see how. So, and so these are actually DMRG calculations that Anna did at 0 temperature first. And so we look at these deviations, and what we do is in every single snapshot that we get, like in the quantum glass microscope, just from theory, we look at string length here, and we basically look at how often certain string lengths appear, okay? And what we do is we start with the ground state, the antiferromagnet with 0 doping, and create a single hole. We just shoot it out, and in this state we ask how often do which guys appear. And this background here, of course, that's just the noise, right? The holes have not moved. So this is our background signal. What you can see is most of the strings have a length of 0. And then you can see there's this structure here. And there's more 2 and 4 and 6 strings than the others. And this is actually easy to understand, because remember, the quantum fluctuations are modeled, these spin exchange interactions. They exchange 2 spins, right? Now imagine you have a hole, and next to it you have 2 spins, which are as they should in the near. But now imagine I exchange those. I suddenly change 2 sides to red, right? So the string length should change by 2 units. And this is why it's very easy to generate these humps at the 2, 4, and 6. And of course, if I combine multiple of these quantum exchanges, then I can also get the, the numbers in between. So there will be a bunch of noise. Okay. So now we understand roughly the background. Now the question, of course, is what happens if the hole is moving, okay? So what we're going to do is so this is the simulation in DMRG, where the holes are now actually moving with some tunnelings, and we increase the tunneling from green to blue, so they become more mobile. And now, of course, the strings should be longer, right? If the more mobile it is, the more fluctuations we have, the longer the strings are. And indeed, you can see that the green one already has more longer strings, but if you take the blue one, you have a significantly more longer strings. So you have this broad background here of many long strings. Okay, and this is basically proof that you have these types of string patterns in your model. Okay, now you can ask. I was drawing all these string pictures before. You can ask how well do we actually understand these strings? Because I claimed that we have a good understanding. Okay, so what we will do now is we're going to cheat a little bit, right? We'll take the snapshots with this hole that didn't move at all, right? Just a pinned hole. And then I'll take those snapshots and then move around the hole in random directions. And the only input I use is I know how likely it is that my string has a certain length, right? So this I calculate from the simple picture. So I know how likely it is to have a certain string length. And then I just include these strings by randomly moving around my strings in the picture, okay? And here's what we get. So, so I basically get a new bunch of fake snapshots. I take these new snapshots, I do the same analysis on these new snapshots, and what we get are these green and blue curves, okay? And, this looks fairly similar to what we saw in the exact numerics, and in fact, if you put them on top of each other, it's actually remarkable how well this works, right? And this calculation that we did by hand was really a semi-analytical calculation, right? You can do it on the back of an envelope. So, and that's really nice, that we can learn something about this complicated doped Hubbard model by just doing a simple calculation and putting these important charge fluctuations into the system. Okay. Now, of course, you can say, imagine you have the actual 2D Hubbard model at some elevated temperature and finite doping. Now I only discussed a single hole, right? But then you would say, well, at some finite temperature, maybe the correlations between the holes are not so great. And we know, at high temperatures we don't get ordered states yet, no stripes. So we can basically just put these holes randomly into the let's say a perfect Néel state and see what happens. And so this is what I did. So this is 25% doping at some realistic string length, and I started from some picture and I messed it up. And so what this messing up, what it means, it's really a form of hidden order in 2 dimensions, right? So the question is, can you see what this picture showed? It's probably a little bit hard, but as you go to lower and lower dopings, yeah, okay, it becomes clear what I started from, right? But that's the key idea of the string picture, right? That just the presence of these charge fluctuations messes up your antiferromagnetic pattern in real space if you measure, but it's a type of hidden structure because if you sort of retrace the strings, you basically still know about this underlying original structure. Okay, so this, of course, is just a toy, right? So now, next I'll show you that this actually also works in experiments. And so that's basically a comparison we did in Markus Greiner's group, and they actually took the experimental images. So I should say there are some limitations. So unlike in the setup that Immanuel Bloch has described, in Markus Greiner's group they cannot yet detect both spins at the same time. So we were a little bit limited. We just saw basically where, let's say, one spin species was, and then what we did is we just looked at those snapshots and basically again looked at areas that are different from what we expect in a perfect checkerboard, looked at the strings, and the first thing we looked at is how many of those do we get. And at zero doping, we already get a bunch of those because we have this background noise, and the thing is they don't really see the holes and the spins at the same time. So we have some background noise. All we care about though is then the change of these patterns with doping. Okay, so and that's these blue data points. So you can see as they dope, they basically see more and more of these string patterns. What's remarkable though is, and what we like, is that again we do the same fake snapshot procedure. Okay, so we take their actual experimental data at half filling without holes, so we know they don't have holes in there, and then we just randomly place holes into these snapshots and move them around with the distribution function we calculated, and then we get this prediction by this geometric string theory here. Okay, so that's this green line, and you can see without any fit parameter, it shows a remarkable agreement with what they measured. Okay, so we're very happy that we can describe this doped Fermi-Hubbard model without any fit up to 30% doping in this quantity at least. Okay, Now, of course, we have to look at other quantities. One thing they did is they looked at even the histogram. So they looked at, this is a certain string length, this is how often a certain string length appears, and again you can see at different dopings. Okay, there's quite some noise, right? So but at least again the string prediction fits fairly nicely. The shapes are pretty similar, so you could say, well, maybe there's not so much information. So the next thing we looked at is, what about the average string length? So we just take this distribution and calculate the average length of these patterns. And this is what we get. Again, as a function of doping, this average string length. And the blue data is here, and you can see this green line is the prediction by the theory, again without fitting parameters. And it's cool, it works perfectly, it describes exactly what we want. Okay, now, if you look at this plot, there's one thing that's really nice, and that's the following. If you look at the structure of the data, it sort of looks like this. It seems to be more or less constant, and then it starts to go down. And so one interpretation this suggests, and I'm not saying that this is a proof, but I'm just saying this is suggestive, is that you have your antiferromagnet and you start to dope it, and in the string picture the idea is you have holes and they have these string patterns associated with them. And if the doping is small, these guys don't overlap, right? So our string length that we see should always be more or less the same, because we basically see all these individual strings. But then of course once we hit the doping where the system is so dilute that the strings start to overlap, then the overlapping strings, they mess up the way we look at these string patterns, right? So basically, one crosses the other, and then it sort of cuts both strings in halves, and therefore the string length distribution should change. And indeed, this is what we see here. And it turns out, if we just do a simple calculation of our strings and ask when do they start to overlap, that's at 15% doping. So this is more or less where this starts to go down, right? And again, we're happy that this is consistent. But I want to really caution, this is not a proof of this type of behavior. And of course the goal is to do similar measurements, maybe at lower temperatures, and then with the full spin and charge resolution that Immanuel has, and many experiments are aiming for, of course. So then of course the hope is to sort of nail this down. Okay, so are there any questions up here? Cool, okay, so then I want to get to the last part. And the last part is about some modern applications of machine learning to these types of problems, okay? So before I get into the details for the Fermi-Hubbard model, let me talk a little bit about machine learning, okay? And how you can use it in quantum many-body physics. So the basic idea, if you want to do machine learning, is you start with some big data set, okay? And a big data set usually means you have input, and the input you can think of as input 1 and so on, input n, right? So you have, and so let's say this could, for instance, be like in these snapshots, zeros and ones, and 1 to n labels all the lattice sites, okay? And so the number of possible configurations of this input is something like exponential in the number of sites, right? So the number of possible inputs is huge. And the idea is, we want to have a machine, at this point it's a black box, that gives us some results, R1 to Rn. And the key goal, of course, is to have m much smaller than n, right? Then the possible outcomes would be something like e to the m. And of course, let's say if our output is only 1 or 2 things, then we learn something, right? Because we have a big input and reduce it to 2 things, right? And of course, an example is if you have a dog and a cat, you give the machine an image, right? It comes in, does something, and gives you its output. This is a cat, this is a dog, right? So you dramatically compress your data. Okay, so this is the basic starting point for machine learning. Of course, so there are 2 things you have to do now to make something like this work, right? Number 1 is you have to train your machine somehow, and in order to do this, you have to basically, the machine should be efficient, right? If you put something in here, let's say some very elaborate fitting procedure, you do your favorite fitting in Mathematica, try to fit these huge numbers here, this is going to fail, right? So it's very important that whatever you have in here is extremely efficient, right? And this is, of course, where the motivation came to look at the human brain, right? So human brain is basically neurons, and they're somehow connected, and so, then you draw pictures like these. And the idea is to connect these things somehow, and all these connections here. so what do I mean with this, right? This is now I'm drawing something that doesn't mean anything. But what I mean with this is actually a simple linear network, right? So the idea is every of these links here are associated with some matrix elements, W, I, N, let's say. And this is, let's say, M1, and N, let's say, right? So this is what people then call the intermediate layer. And you basically have matrix elements, W, I, N, and these are just numbers, okay? So you have a few numbers, but you know, the number of entries in W here scales with N, not with e to the N, right? So this is, let's say, small. This would be like the number of pixels, maybe squared in an image, so this is a number we can handle. And then the idea is to simply say that the output here should be some linear combination of inputs times these matrix elements, times and maybe with some offsets, right? So the results would be, for instance, result I is going to be something like, let's say, this is the first layer, this is the second links here. So this Ri here, for instance, would be W2 in this case. We go to I and we come from the intermediate R and we sum of all these intermediate R's, all these indices, times the value of these MRs plus some offsets, BRs, and these MRs in turn, those ones here are also linear combinations of the ones here, right? So that's basically, it's linear algebra, right? That's the take-home message. And then it turns out that there are some very nice optimization schemes that you can use for these networks that very efficiently generate get you from here to here, okay? And the nice thing is you don't even have to do it yourself. You can take the predefined Google or so machines that do the optimization for you, okay? So and of course the computer science people have optimized this, right? So they have really good procedures to do this. Okay, so what this gives us then is something where we train the network, and with training we mean we give a sample set of data as input, a few out of these very many configurations. We use this input training data to optimize these W's in such a way that they always give the desired results, right? So we would take hundreds of pictures with dogs, hundreds with cats, and tell the network, those are cats, those are dogs. We send it through the network, and we optimize these W's so that it, and most of the times it actually finds the right output. It says, okay, this is a cat, this is a dog. And so maybe one comment about the output is, these are numbers, right? So these guys will be numbers. In fact, you can make it such a way that these I's are basically between 0 and 1. So you can think of those as probabilities. And then you decide which one of those you take by choosing the one that has the largest probability. So in some sense, the network even tells you how sure it is, right? It could be that some images are exact, it's very likely, it says, oh, this is clearly a dog. In others, it says, it tends to be a dog, but it's not exactly sure. And then these two numbers will be closer to each other. Okay, I don't want to go into more details, but now I want to basically discuss some physics applications and show you some of the things we did there. So maybe before I come to what we did with the Fermi-Hubbard model, some general remarks. This stuff is very useful for several things, right? And I think the community is just starting to explore for what problems exactly is very useful. One obvious application in hindsight is that, for instance, if you give the system some data and you want to recognize where's the phase transition, right? You give it some data from one phase and from the other, and you teach it to distinguish two different phases. So that would be basically characterization of your phase diagram. And that's one thing people do. Another interesting thing, very exciting, is you can think of this as a way of representing quantum many-body states, right? Because what you have is you have some input, and those would be your, for instance, these spin states, where the holes are, where the spins are, and then what you want to get as a result is basically your wave function, psi of all these input, right? And now, of course, you can train a network that efficiently generates you the value of this wave function. Okay, and in that case, these guys would become complex, but it's not hard to make these guys complex, and so this also works, right? And this is a very promising future direction, I think, to represent many-body wave functions. So what we did here and want to do now is to apply it to distinguish different correlated states of these systems. Okay. So the starting point is we have three different sets of snapshots, and I showed you, okay, this is the experimental data. In our case, we take the stuff from Markus Reiner's group. So it's a bunch of data. We have this geometric string theory stuff, and as I told you, we take those experimental data and put these holes in by hand, so we can generate a bunch of our fake data, if you will. And then we have a third set, which is one of these RGB states. So I don't want to go into details, just tell you this is some approach. We included one fit parameter to make the nearest neighbor correlations match, but that's another theory ansatz you can use, and you can generate these snapshots. Okay? And our goal is to ask, can we distinguish these three from each other? How different are they? And traditionally what you would do is you look at correlation functions that you can just measure in all of these data sets, and you look at how different they are. And so this is nearest neighbor spin correlations as a function of doping. And so the blue stuff is the experiment. This light green line down here is our string ansatz, and this the dashed line is this RGB state. Okay, and you here would say, the RGB actually works better, right? The string stuff is not so bad, but it's, there's some clear deviations. We can do the same for the diagonal correlators, and now I would say the string works better. It actually predicts a sign change over here, whereas the pi flux, this RGB thing, does not predict a sign change. But if you actually look at the quantitative values, they're fairly close. Okay, so at this point it's hard to tell. We can also look at more non-standard quantities, and this would be a measurement of this staggered magnetization. In fact, this is what I showed in the very beginning, just with doping, right? So this is the total staggered magnetization, and this is the number of counts we get. So we take images, and in each image we calculate the staggered magnetization, and we see how often do I get a certain value. So this greenish stuff is, the red stuff is the experiment. It's a broad distribution. And if you look at the strings and the pi flux, it's basically impossible to distinguish them, and they both match the experiment, right? And, in some senses it's even disappointing, right? We look at something so complicated, and it still looks the same for all the theories, okay? But this means it's really a challenging task to distinguish these different theories, right? And so what we do now is we do machine learning, and we try to distinguish them in some way. And, so here's what we do to be a bit more precise, right? So this would be an example of a snapshot. So the pixels are cut out like this for some experimental reasons. And the first step to get some input here, right, for these eyes is you basically take masks, MI, and you basically convolute these masks with your actual data. And this is something that people also do when they distinguish cats and dogs. It turns out to be very efficient. And then we take all these convolutions into this matrix, and that's basically the input that we put into the network here. We draw these connections, and we get some categories out, and that's the output over there. Okay. And then this network runs. Okay, so now the first thing we do is we basically learn it to distinguish all these three data sets. And that means we basically have as possible input experiment, strings, and this pi flux thing. Okay? And so what I'm plotting here is now, after training this network, we take some data that we left out before. So we did not use the data that we now use for training, right? That's important because if you're already trained with some data, it of course will favor certain directions, right? So we take data that we didn't train with before, and we put this in, and we know where this data comes from, right? For instance, there would be snapshots from the experiment, and then we ask the machine which of the outcomes or in which class would you put it, right? And if we take the experimental strings, so the experiment goes to, for some 40% into the experiment group as a result, so that's the outcome. Some other more or less, maybe 35% to strings, and some 25% to pi flux. And if you look at the strings, it goes sometimes to experiment, sometimes to strings, and sometimes to pi flux. And if we look at the pi flux, in more than 50% of the cases, it actually goes to pi flux. And if you just look at this like this, you would say, in fact, the machine has some difficulty distinguishing the strings from the experiment because these two look fairly similar, and whereas it has an easier time distinguishing the pi flux from strings and experiment. Of course, this is not perfect, right? If it could completely distinguish them, you would have just pi flux here, just strings here, and just experiment here. And there's certainly the experiment goes to experiment a little more often than strings, but not so unexpected. But there's some confusion here, right? And that already tells you that strings and the experiment should be fairly similar to each other. And so this is something done now at one fixed value of the doping, right? And at each doping we have all these data sets. Now we actually repeated a similar procedure, not exactly the same, at different doping values. So what we do now is we only train the machine with two of the theories, right? So we only train it to distinguish this string theory from this pi flux. Okay? So it only knows two categories. We train it, let's say, at 4% doping, and then we take the experiment and ask the machine to classify the experimental snapshot as one of those two categories. And then it gives us some output. Okay? And then, of course, this is something we can repeat at the other doping value. And the machine runs for a while. And then this is the outcome, okay? So I'm plotting here the doping. You always take the experiment, ask where it goes. And the blue one is the probability to go into this string data. And you can see it does like this. And the other one is the pi flux. And of course, okay, so of course, one of them is the other one mirror symmetric with respect to this line. And what you can see is up to something like maybe 12% doping, I would say it clearly favors the string approach. And one thing to note is this probability is really on the level of a single snapshot, right? And that's quite remarkable because every snapshot also has quantum fluctuations in it, right? So it's not like a cat or a dog, but it's always some quantum thing, right? So the fact that we can get something like 70% on the level of a single snapshot actually means that if we would give the machine not one, but let's say 10 snapshots, it would be much more certain that this entire set of 10 snapshots is actually in this string class. Okay, and then I would say, okay, here it's completely confused, and okay, here it seems to favor a little bit the pi flux, but it's also fairly confused over here, right?
Can I ask,
yes.
So
Yes.
is the memory data anything else they subtracting or not?
No. This is the bare data. I think okay. So I think it's no subtraction. No. I think there's some post selection to the best maybe 30% or so of the staggerization. But we also check that if you do it without post selection, you do get smaller numbers. But why? Well, the motivation is that the way.
Post selection staggered manipulation is not a globally conserved quantity. It's dangerous, no? Post selection staggered manipulation is dangerous.
It can be dangerous. I would argue as long as you don't post select on a microscopic data set, right? It's still representative for the entire set. And we take a large percentage of these cases. Yeah, some.
If you pick out, if you are, then you apply right in your favor, of course, TJD solutions, then you are favoring string solutions. So I'm worried.
Yeah.
This is not a fair way of comparing things.
One has to be careful, but that's true. We find the same signature though if we don't post select, right?
Yeah, but then you should not those. Because I really think it's very dangerous to do that. Because if you sub-select certain MZ values, I don't know which ones you favor the ones maybe in the direction of the TJZ model, and we know the string model was better for the TJZ model,
Yeah.
it's better, then you are of course favoring, what you will get is to favor string model, because that fits better TJZ, so I think this is very dangerous.
Well, yeah, I agree. One has to be careful. That's true. But it's still, I think, it's a meaningful comparison between the states.
Yeah, I would just say don't do that.
Yeah. I mean,
let's say when you generate string, you actually take the data from Optical, which has a lot of quantum fluctuation.
Yeah, that's true.
That is not possible. Therefore, sort of the same bias
Yes.
is in the theory as,
Yeah, but just don't do any bias at all. I think you don't want to compare it with just have experimental data, right? And I don't want to bias it into certain, why should I sub-select a certain standardization value? That's very dangerous because you're throwing out quantum fluctuations of the problem.
Well, the motivation.
I could post-select on staggered magnetization -1 or +1, and then it would be a perfectly else state. And then you say, oh, I analyze that, and then of course what you get is be agreeing with perfectly else state. But that's not the physics you have in the system. So
That's true.
So that's my point in the sense that it is.
well, I guess maybe the answer is that if this experiment had spin resolution, it would be
Fine, but they don't have.
So when you
Okay, fine, but they don't have, and then I think post-selecting don't, then I would say the best way to analyze the data is to not post-select on staggered magnetization. Just show that if the contrast is smaller, well then that's what it is. But I think this is biasing data in a very dangerous way.
So yeah, one has to be careful. I mean, the motivation to do it in the first place, of course, is that we are afraid of the noise that comes from spontaneous symmetry breaking, sort of, right? Which is sort of not exactly this quantum noise that one would think of, right?
Yeah, but this is really manipulating the data data in a, I think, not completely sound way, actually.
Is this particular one also?
I think it was, yeah.
And if it just gives a lower amplitude, then that's what it is. I mean, let's just show the lower amplitude and say, okay, then we cannot make such big claims that we can distinguish between pi or geometric strings, and it's just what it is. But I think, and I don't know, I think we have to be very careful with this.
One has to be careful, I agree, yes, yeah.
I don't like this, I mean, you know, we discussed this about our data, but I don't, especially on style amortization, there's always part of one path, and that's really not so good.
Yeah. Okay, so that's actually the last slide. Yeah, so you know, I showed you this last time who was involved. So thanks again.
I've seen this talk before, so that's why. So, more questions. Very interesting.
So, if I were just trying to distinguish two distributions, like naively, I would potentially look at the cross entropy between the distributions. Do you just not have nearly enough samples to meaningfully do the cross entropy? Or what is the...
We didn't really think about it yet. I think it's a good idea to also do those types of comparisons. Of course, you know, here the goal was also to see if we can learn if the machine learning is sensitive to these patterns, which we saw before that there's some way of distinguishing them. But yeah, that's another good idea. Once you do that. And it's also true that the number of snapshots you have is not huge, right? Yeah. Compared to the actual number of possible snapshots.
Right. Yeah.
So it's in the thousands, basically.
Other questions for Fabian? Okay, then join me in thanking Fabian.